So hello everyone, and welcome back, and welcome to an old friend, Timothy. and Timothy is at Shawnee State University, and he has been with us for Astronomy for Archival Data, as well as now AstroSprint. And like he knows in the Star Trek, in the Star Trek theme, this one is Enterprise, then we have Discovery, and then we have Next Gen. So we hope that you'd be there with all of us for the remaining episodes. And so I'll give it over to Tim. And Tim, you are already co-host, so you can, you can share your screen and start. Welcome.
Okay. Now let me see here. I've got. I'm going to load up my PowerPoint, and so I've got to hit. Let me get the PowerPoint on first. All right. Let's see how this works. So how do I do the share screen?
So there's a green button down. You can see in the Zoom window, there's a green button.
Oh, yes. Okay.
And you open your PPT or whatever you can share your desktop or your screen or whatever you want, right?
Okay. I'm going to try doing, I've got two monitors here, which should make it easy.
Yeah. Yeah.
All right.
So we can already see your PPT.
Okay. Now, if I can, actually, if I move this here, and then y'all will see the. All right. Now, is the title page coming up there?
Yes. Yes. Now we see your PPT, spectroscopy of AGN, right?
Yes. All right. Now so when I had first looked at this, I was thinking of doing a very general talk on AGN spectra. And I realized that in order to get you all some background for projects, I'll give you a brief overview of how AGN spectra look, and then we're going to go into applying it to measure the black hole masses in these active galaxies, which is a great application. It's one that I'm doing right now for a paper, in fact. The background on this picture here, by the way, these are 320,000, I believe, quasar spectra from the Sloan Digital Sky Survey, from the BOSS survey, BOSS. And what you see is that they are stacked up. It's just each horizontal line there, each stripe, is one quasar's spectrum. And you can see from the color coding, you can see bright emission lines coming from these. These are labeled. And as you go out to higher redshift, farther away, the Doppler shifting pushes those farther and farther to the right, which means redder. That's the red shifting. And it's really interesting to see how those lines move over, and in many cases, how they evolve, where you see some stronger and weaker. Let's go on then. I'm going to do a brief review of how spectra are formed. For those of you who haven't done spectroscopy before, Kirchhoff's laws. You may have come across Kirchhoff's name for radiation, emission and absorption of radiation, and also, if you've done any electronic circuits, Kirchhoff's loop rule and Kirchhoff's junction rule for voltages and currents. Same guy. So there are three basic kinds of spectra. These are for optical spectra, I should say, meaning for visible light, and it also applies in the ultraviolet and the infrared. There are some different things when you get up to X-rays, gamma rays, and all the way down into radio. There are different kinds of formations of spectrum. But the three that we'll be concerned with here are in A at the top, you see a hot, dense gas, or a hot solid or liquid. Anything that's dense will produce a continuum spectra. So a continuum spectrum emits, well, all the colors of the rainbow, very much like what you normally see from the sun spectrum. It will be produced as a black body radiation curve according to the Planck law. And so we've got the color coding there on the right. So we're going to plot the intensity, which is also the flux density. How much light do we see per wavelength? And in optical spectra, we typically graph the spectrum by the wavelength rather than by frequency, although it can be done by frequency as well. The second kind there down is if you have a hot, thin gas, low density gas. In that case, you don't get the continuum spectrum. Instead, you get individual emission lines. And we can see some of those here. Here they've given the example of hydrogen gas, and I'm going to show its spectrum in a moment. And so you'll have the bright emission lines superimposed on top of a dark background. In the third case, if you have a thin, cool gas, so low density gas, but not hot enough to emit much light of its own, but you illuminate it from behind with a continuum spectrum, in this case from a light bulb, but it could also be from a star, then you will get the stars, or whatever the continuum spectrum is, the continuum spectrum with dark absorption lines, lines that are removed from the spectrum. That is, whatever lines that gas would have emitted when it's hot, it absorbs when it's cool. Of course, in practice, every gas has a temperature above absolute zero, so it emits some light, but it can absorb light that's coming through it as well. In astronomy, we tend to use a little bit different notation than the chemists use. So let me show you some of our quirks here. We're going to use angstroms, named for Carl Langstrom. I believe he was a Swedish physicist. The angstroms are going to be our wavelength units, and we'll use the Greek letter lambda for wavelength. Again, I'm sure many of you have gone way beyond this material, but this is just a review for those who haven't done any spectroscopy. The angstrom is 10 to the minus 10th meters, and we will tend to use that more often than we do nanometers, which are 10 to the minus 9th meters. So if you see, sometimes you'll see spectra in nanometers, and you'll just have to multiply by 10 to get the wavelength in angstroms. Putting the wavelength in angstroms means that we don't have to worry too much about decimals for a lot of uses. Common lines that we will see are the Balmer lines of hydrogen. Those in astronomy are labeled with H for hydrogen, and then a Greek letter, alpha, beta, gamma, and so on like that to go through the lines in order from the longest to the shortest. The longest of them is hydrogen alpha, or simply H alpha, with a wavelength of 6,565 angstroms. Then H beta, the second line, a little bit less intense, is at 4,863 angstroms, and so on. And we go to shorter and shorter wavelengths as we go down the list there. Now, you'll also see the alpha, beta, gamma, and so on notation applied to, say, the Lyman series, Lyman series in hydrogen, which are ultraviolet lines. And for those, you'll see capital L, lowercase y, and then the alpha or beta or so on. So for the Balmer series, we just put H for hydrogen. And these are the brightest optical lines. You'll also see what are called forbidden lines. Those are ones which would be forbidden by the first approximation in quantum mechanics, but they really do that. They're not absolutely forbidden. They're simply less likely than these so-called permitted lines of the Balmer series, the Lyman series, the Paschen series, and so on like that. The forbidden lines are seen in space, but not in the laboratory. The reason is that in the laboratory, we don't have a good vacuum. Even the best vacuum we can produce in the laboratory is many times, orders of magnitude denser than what we get in gas clouds like a nebula in space. And therefore, these forbidden lines that would take, it would take the electron a very long time to drop down to a lower level to one of these forbidden transitions. In the meantime, in a chamber on the Earth, we would wind up having collisions between the atoms that would occur before that would happen. And these collisions will collisionally de-excite that electron, and it will simply go down by another path, and we don't see the forbidden line. So these forbidden lines are distinctive of low-density gas clouds in space, and we will write them with square brackets around the element name, and then we're going to put a Roman numeral to tell us how ionized the element is. For example, O3 that I put down there, Roman numeral 3, that means that there are 2 electrons removed, doubly ionized. Roman numeral 1 means neutral. Okay, so you'll see H1 is neutral hydrogen, and you'll see those permitted lines like the Balmer series are H1 lines. Ionized hydrogen would be H2 because it only has one electron. So oxygen 3 has a bright emission line at 5,007 angstroms, and because the bracket notation is only telling us the element and the ion, then it doesn't tell us which line. And so you should specify which line with a lambda and the wavelength in angstroms to the right. Nitrogen 2, there's a bright line at 65, 63 angstroms, for example, but of course there are others as well. The one problem is when you're reading papers is sometimes the people working on one subfield in, say, active galaxies might not put which line they mean when they write O3, and you're just supposed to know, oh, of course we mean O3 5007 or into 65, 63, but there are others, and you might have to dig through the literature. All right, so let's take a look at what some different kinds of spectra are like. Because if you're looking at an active galaxy, it is a galaxy for one thing, but it has that active nucleus superimposed on it. Well, galaxies are made up primarily of stars. So what are stellar spectra like? You see here at the top of the graph, where we're plotting again the intensity with arbitrary scaling, and then wavelength, in this case in nanometers. We're going to have the blue side, short wavelength to the left, and the red side, long wavelength to the right. So we have the bright O and B stars at the top there. You see that they slope up and to the left because they're very blue. So the continuum here is what dominates. And then you have absorption lines superimposed on that from the atmosphere surrounding the stars, which are cooler than the surface. As we go down to cooler stars there, you see that there's more absorption on the blue side. As we get hydrogen lines come in there, you can see the Balmer series, in fact, which are not labeled, unfortunately, here. But on the A2 star and the F0 star, you can see that the Balmer lines are the ones that make that series that converges over to the left, and where the Balmer series converges, there's a limit. That's called the Balmer limit. Then we get a lot of absorption on the blue side of that, and that makes it the star a little bit redder as a result, because there's simply less blue that makes it through. When we get down to the cooler stars, we get molecular lines that show up. The stars themselves have a redder continuum, and they have a lot more absorption as well. We also get a distinctive absorption at 4,000 angstroms or 400 nanometers from the K and H lines of calcium. Let's take a thin hot gas like a planetary nebula. It has very little continuum, although this one might have the continuum subtracted here. But the continuum in general will be very faint. So it's why it's flat and dark here. And we have the Balmer lines of hydrogen. We see H alpha over there to the right, H beta in the middle to the left, H gamma, delta, and so on down the list there, which get fainter and fainter as we go. We also see a helium-2 line, and then you see a couple of prominent lines of oxygen, oxygen 3, which are very close to the hydrogen beta. We're going to be using the H beta line for our black hole measurements, and those O3 lines can be a problem. You also see that next to hydrogen alpha, there is a nitrogen 2 line, which is almost blended with it in this case, and it will be very hard to disentangle from the H alpha line in a quasar. Now, active galaxies are then a combination of all the different stars in a galaxy. The bright, hot stars that are very young, those O and B stars, and a whole lot of the cooler, redder stars. The combination of all of those then leads to a kind of a broad continuum of galaxies superimposed with absorption lines from the different stars. Now, because you have different stellar populations, you'll have a few stars that are very young, and you'll have a lot of stars that are older because let me make a note about that. When you generate a bunch of stars all at once, you'll get a few massive stars and a lot of low mass stars. As a result, Those massive stars, which are going to be the hottest ones when they're on the main sequence, they're so massive they burn out more quickly. And so soon after a burst of star formation, the hot blue stars move off the main sequence, and you have less of the blue light. So as a population of stars ages, it starts off very blue, and then it moves over to being very red later on. And we can use that to get a rough age for the galaxy. Now, that makes some complicated lines on there for the galaxy, but on top of that, for the active galaxy, we have a bright blue continuum. If you take a look at this one here, now, oops, I didn't mean to go to that other one just yet. All right, you see the continuum is sloping up and to the left, down and to the right, and this here is mostly from the quasar nucleus. This is actually an average, a composite spectrum of several different quasars, from 16,000 of them. And quasars are very blue. I'll show you the structure of them in a moment. And we see superimposed emission lines. You might occasionally see some absorption lines from the stellar spectra lying underneath this, but this is dominated by the emission lines. H alpha here, H beta and O3, and you can see that nitrogen 2 here, right there. And then we have a few others going up like that. All right, let's take a look at the Balmer lines in hydrogen when we see them in a quasar. Actually, sorry, this is from a star, but I wanted to show you what they look like when you're not in a nebula. All right, this is an emission line star there, and you can see how these Balmer lines approach a limit. There's an asymptotic limit right about there. That's the Balmer limit. All right, now let's take a look at zooming in on the H alpha and the H beta lines in a particular quasar. It has the beautiful name of J091702.11 plus 212337.6, which rolls right off the tongue. Now, that catalog name there, J, stands for the, it's a marker for the coordinate system centered on the year 2000 for right ascension and declination. And then we have the right ascension on the left and the declination after the positive sign there. So it's just a coordinate name. And this is from the Sloan Digital Skies survey. Now, we can see here that there's the continuum. It's blue, so it's higher on the left side, lower on the right. And the dashed blue line is their fit to the continuum. It tends to have a power law continuum when you plot it in terms of frequency, but we're plotting in terms of wavelength here. So it looks more or less like a flat line over a short range of wavelengths, but if it would curve over a longer range of wavelengths. Now, we have the H beta line here, a couple of oxygen 3 lines. Then we have the H alpha line here, and we can barely make out the nitrogen 2 as a little blip up on the shoulder. If we zoom in on the individual lines, H beta here, look what we've got. We have a broad line here, which is more or less a Gaussian. There are two basic line shapes we can fit. A Gaussian, which is the bell curve, which is kind of what you should go by default, unless you know better. And the other kind is a Lorentzian function. And that has looks a little sharper, a little more sharply peaked. This one might be a Lorentzian, and there are some other things that you can do with them too. They can be asymmetrical, for example. The blue on the left and the red on the right don't seem to come down quite at the same slope here. But notice that in addition to that broad emission line, we also have a narrow one that's superimposed on it. That's the little that sticks up here in the green, and that's the red model there. So we have both broad and narrow kinds of lines. Notice that the forbidden lines are only narrow, that's red. Whereas the permitted lines, the Balmer lines here, are mostly broad with a bit of a narrow contribution. Take a look at the hydrogen alpha. Here we have a narrow contribution to H alpha plus a narrow nitrogen 2, both on the left and the right. And then we have some sulfur over here way off to the side. But mostly the H alpha is the broad component there. Okay, so why do we get broad and narrow, and why do we get a continuum all from the same beast? Well, an active galactic nucleus, or AGN, is at the center of an active galaxy. And this is from Megan Urey. from Meguri and Paolo Padovani back in 1995. They came up with this diagram, which everybody has copied for the last 25 years, 26 years. We've got the black hole in the center. Now, this is a cutaway view. You see this big ring around it there. That is the dust torus. Torus just meaning a donut shape. And immediately surrounding the black hole is a moderately dense accretion disk of gas that is accreting onto the black hole. And there's my cursor, right? That is going to produce the bright blue continuum, which is mostly in the ultraviolet and the visible light. Surrounding that, we have these gray clouds here. These are hot, thin clouds of gas, which will be of hydrogen, oxygen, and many other chemicals, whichever elements are found in the center there. And those are orbiting close to the black hole. Now, because they are close to the black hole, they get irradiated with the ultraviolet light from the accretion disk that will ionize the parts of the broad line clouds, and they will fluoresce. The electrons will bump up from the ultraviolet light, then they will jump back down, emitting longer wavelengths of light in an emission line spectrum. Because they are close to the black hole, they're orbiting at high speed. Because they're at high speed, they are Doppler shifted. Now, farther out, we have those little black dots. Those are the, let's see here. Oh, no, farther out here, we still have them in gray. We have the narrow line clouds. These are farther away. They have the same processes going on in them, but they're farther away, so they're orbiting more slowly. And as a result, they are not Doppler shifted as much. We also have the jets in about 5 to 10% of cases there, which are plasma jets moving at near light speed, and that produces synchrotron radiation. But we won't get to that here. Now, I've made a diagram to show how these broad line clouds can be used to measure the mass of the black hole. Let's say we've got two of these clouds, one orbiting, and they're orbiting in a circular orbit, as a simple approximation, one orbiting towards us, the other moving away from us. Now, the observer marked on the right here, that's really a side view of our eye, but it's the normal physics symbol for an eyeball there. It's kind of an odd thing. It's very abstract. All right. Now, let's put in the math on here. We've got a black hole at the center, and I've labeled the mass of the black hole as m. We have the broadline clouds orbiting at a radius r in a circular orbit, and they're orbiting with a velocity v, and the mass of the cloud is a lowercase m. The cloud that's moving towards us has light that is blue shifted. That moving away from us has light that's red shifted. Now,
Jim and Brenda Hamilton. Brenda Hamilton.
Hang on just a second here. Got a call that might be important. Let me get this to my wife. Hello? Hello. They are in the let's see, they are up the stove. Hold on, I'm in a talk right now. Can I give you a call back in a bit? Okay. Great, okay. Bye. Okay, sorry about that. My parents are very elderly, so anytime the phone calls from them, I'm always expecting a problem. But it turned out Mom was just looking for the cereal for breakfast. She'd forgotten where I'd put it. Okay.
No problem.
I'm very glad. Yeah, Dad has been in poor health lately, so we're worried about him falling and hurting himself. Okay, so let's see. So here, we're just going to apply basic introductory freshman physics. You might remember of Kepler's laws of planetary motion. Well, that comes from this, from the orbital mechanics here. And so if we've got Newton's second law, force equals mass times acceleration, the acceleration in this case is inward, radially inward. And so that's the centripetal or radial acceleration. minus v squared over r, where the minus sign means it's in the negative radial direction, meaning inward. The force in this case is simply Newton's gravitational force. We do not need to apply general relativity, Einstein's law of gravity, to get this to work. Even though we're dealing with a relativistic object, a massive black hole, Newton's law of gravity works perfectly well. So that's minus g, the gravitational constant, times the mass of the black hole, times the mass of the gas cloud, divided by the radius squared. Putting those in on the left and right sides, we can solve for the mass of the black hole, and we get rv squared over g. Okay, now, how do we measure that with what we can observe? We don't have direct access to the radius nor to the velocity of the clouds, but we can get them indirectly by measuring, if we can measure the radius of the broad line region where all the clouds are, and if we can measure the velocity from the Doppler shifting, then we can get the mass of the black hole if we account for the fact that this simple model may not really be true. You see, the gas clouds may not be orbiting in a perfect circle, all lined up in the same plane. And we might not be viewing it from the side, from within the orbital plane. It could be that we're viewing it at some angle. Maybe we're viewing it from face on like this. In that case, we need to account for this, what's called the Varial factor, lowercase f. So that Varial factor, if you have a spherical distribution of clouds orbiting in all different planes, all in circular orbits, that Varial factor will work out to be 3/4. If you have it where it is a flattened disk, then the factor will be different. And if you're viewing that disk from, say, closer to the pole, then that Varial factor will be a higher number, could be greater than 1. For some of the active galaxies I use, they've been assuming a factor a little more than 3, for example. We're reviewing them from nearly on the pole. But so that's exactly what that Varial factor should be, is often a big topic of debate. But we'll use 3/4, which is a good average number. Now, how do we get the radius of the broad line region? Well, from a technique called reverberation mapping, which is a very accurate way of measuring the mass of the black hole around a galaxy, around an active galaxy. What they do is they wait for eruptions in the black hole, for that accretion disk to go through a flare where it emits a whole lot more light. Well, the hotter regions of the accretion disk are close to the black hole, and so they receive that flare first, so that the flare first erupts in, say, the ultraviolet. And then as it propagates outward at the speed of light, you get the flare going on into the blue, and then into the yellow, and then the red, then the infrared, and so on. And there are delays between the flares observed at different wavelengths. We can use this to relate the, to calculate the mass of the black hole. But it takes a lot of observations, and it takes an active galaxy which is going through these eruptions. It's a long time, and very few galaxies have had their black holes measured by reverberation mapping. But luckily, many years ago, they found out from this technique that the radius of the broadline region could be correlated with the luminosity observed at 5,100 angstroms. Now, why 5,100 angstroms? Well, that's a region of the spectrum which is generally free of emission and absorption lines, so we can see the continuum there. Now, the way that I've got it written here, the logarithm of the radius of the broadline region divided by a light day. That's the distance light travels in 1 day. And because these are on the order of a few light days, that's a convenient unit of distance, is equal to blah, blah, blah. Now that first additional, the additive term there and the multiplicative factor here are all correlated to different kinds of galaxies, and I've chosen them for Seyfert galaxies, which are kind of like low power quasars. And you can look up, I'll give you references to where you can look these up where you might use for different ones. Now, times the logarithm of, what is all this mess? Well, lambda L sub lambda at 5,100 angstroms means L sub lambda is luminosity density per unit wavelength. That is, how much luminosity per unit of wavelength. And I'll get to that in just a little bit as we go through the steps. Then you multiply it, because that's not luminosity, that's luminosity density. To get luminosity, you have to multiply it by the wavelength. So you take the luminosity density from the spectrum plot at a wavelength of 5100 angstroms, and you multiply it by that wavelength, which is 5100 angstroms. Now, that'll get you a luminosity in units of ergs per second. Many of you may not be experienced with using ergs for energy. Ergs is the unit of energy in the CGS version of the metric system, where we use centimeters for length, grams for mass, and seconds for time. In the CGS system, the erg is the unit of energy instead of the joule, but it's defined in the same way, whereas a joule is a kilogram times a meter squared per second squared, and erg is a gram times a centimeter squared per second squared. And we use those when we do spectroscopy. So that gives you ergs per second, and it's going to get you something a few times 10 to the 44th power ergs per second. So we calculate that in the numerator, divide by 10 to the 44th ergs per second in the denominator. That drops out the units, makes it dimensionless, and it drops out that large factor, and then we get a nice, easy number to multiply through there. Of course, that gets us the logarithm of the radius in light days. So we exponentiate to get the radius in light days. Then we convert light days to meters. Now we've got it in the MKS units that we're going to want. We'll get the velocity of the broadline region clouds with a crude approximation. That is for Doppler shifting, where we have some moving towards us, some moving away from us, and some that are moving in between. Very roughly, the full width at half maximum of that hydrogen beta emission line will be the velocity of the clouds. Now, what do I mean by full width at half maximum? You see, if we've got an emission line like this, and I've drawn it as a Gaussian here, at the bottom is the continuum, that's the base of the line. And where it reaches a peak, that's the maximum flux there. If you go down from halfway down from the maximum to the base, that's half maximum, and you measure the width in terms of the wavelength here, from the left to the right, and that is called the full width at half maximum, which is simply abbreviated FWHM. Now, that when you measure it from the spectrum, that is measured in terms of the wavelength. I mean, it's just delta lambda from left to right, and that'll be in angstroms. But we can convert that to velocity using the Doppler equation. All right, at this point, I'm going to go through, I'll continue with the live demonstration. All right, let me close up my PowerPoint, and I have sent Priya a copy of the PowerPoint there, and I think she's distributed it. Now, I'm going to pull up, let's see here. First, we're going to get a web page. We need to get a spectrum. So let me pull up a blank web page. Okay. All right, so we're going to go to a website called the NASA Extragalactic Database, and that is at ned.ipac.caltech.edu. Now, let me see here if I can open up the chat window, and I'm going to do this, send this out to everybody. There's the link. All right, this has, it's an archive and a catalog of just about every object that is known out beyond the Milky Way, and a few that are inside the Milky Way. So we're going to put in the brightest quasar and the very first one discovered, 3C273. That's the third Cambridge Radio Survey, object number 273. And you just type it into the object, the search window there. You can also put in coordinates, right ascension declination. If you just click on search options, you'll see it gives you help on all kinds of ways to do it there. We start off with a summary page, which has the most basic useful information for it here. It has different catalog names, many different catalog names, and that's only a small selection of them. It has the spectral energy distribution, which is like a low resolution spectrum. If you click on here, you can get pictures of it, coordinates, redshifts, and so on like that. First of all, let's make sure that we came up with the object we intended. If I look at classifications, it says QSO, quasi-stellar object, which is like a generic name for quasar. Flat spectrum radio source, that tells you what kind of radio emission it has. We want the redshift for one thing. Okay, we're going to write down that redshift, Z, heliocentric redshift, meaning its Doppler shift from the expansion of the universe measured relative to the sun as a reference point. And this is a dimensionless number here. 0.158, all right? That's roughly telling us it's moving at about 16% the speed of light away from us. Anything less than a redshift of 0.3, you can approximate that as the fraction of the speed of light is moving away from you. But we can get redshifts that are well over 1. It's just that that's an approximation for low redshifts. Now, we want to get the spectrum, the optical spectrum. So we click on spectra. There are 27 spectra available. They will list them in order of wavelength, from short wavelength first. Here we have ultraviolet. This is the Lyman alpha forest, is something that, well, we won't get into that right here. It gives you what the short and the long wavelengths are in angstroms. Now, what wavelength do we need? Well, we need to get the H beta line at 4863 angstroms, and we need the 5100 angstrom continuum. So to calculate that, we need to find out at the redshift of this quasar, what are the wavelengths of H beta and the continuum. Now, the equation for that, I'm going to bring up a chapter from my book, which I have also given to Priya there. Now, this is a rough draft of it. I've got the first page of this book, of this chapter. It just says, it's the background stuff that I showed you in the PowerPoint. So let's make this a bigger picture. I'm going to go to full width there. All right. And the equation for the observed
Sorry to interrupt, Tim. I have the PPT, but I do not have the chapter. So
okay. Let me see here.
So please share it on the chat window. Yeah.
Okay. Let's see. I believe I sent that to you just after I sent the PowerPoint. It says Black Hole Mass Chapter Draft 1.
Okay. I'll check it. Gotcha.
Okay. So the Doppler shift equation for small shifts, the observed wavelength is simply, actually this applies to all shifts, is 1 plus Z times the source wavelength. Source being what's emitted, observed being what we see here. So that factor of 1 plus Z appears over and over and over when we do these calculations. Now, so in this case, source is 4863 angstroms for H beta and 5100 angstroms for the continuum region. So we're going to need a spectrum that covers both of these. So we get out the calculator. This one was at a redshift of 0.158. So 1 plus Z is 1.158. I multiply it by 4863, and I get the H beta line will be at 5631 angstroms, and the 5100 will be at 5100 times 1.158. And that is going to be at 5905. So we need to go from 5600 angstroms to 5900 angstroms. All right. So these first two don't cover it. Now what about this? That's optical, it says. But you see, it doesn't go all the way up to 5900. That's not good. Now the next two both cover it. This one covers H beta from 4008 angstroms to 8100. That covers everything. This one covers the same range here. All right, so which one do we choose? By the way, the next one is too far to the red. So which one of these do we choose? Well, the resolution is important. You see, this one has a resolution of only 20 angstroms, meaning that you can't find any details smaller than 20 angstroms, whereas this one can get down to 8.5 angstrom widths. So we're going to go with this one. However, keep in mind that even high resolution spectra, they could in some cases be very noisy. meaning there's a lot of random error up and down on the spectrum there. And that could make it hard to measure what you want. So in some cases, you might go for one with lower resolution, but lower noise. We can get a preview of it to see how good it looks by clicking on the picture. And we see, yep, right there, that's H beta. There's the O3. Here's H alpha, and there's the nitrogen 2. So there it has exactly what we need, and it looks good and smooth. So we're going to download that. Now, what format do we download it in? We've got 3 formats available here, and sometimes you have, 4 formats. Oh, there's FITS, which says is not available. FITS is Flexible Image Transport System. We use those for astronomical images as well, but it can also be used to store data tables like a spectrum. Tell you the truth, I don't find much value in doing it in FITS because it's just a list of numbers and you'd have to write a program to extract the numbers. Let's use it in ASCII. Now, the author has supplied it in one format. NED has standardized it in another. Let's use the NED version because we know what that's going to be like. So NED ASCII. ASCII, American Standard Systems for Computer Interchange, something like that. But it's the basic text format. Now, see what we've got here. It is simply a data table. On the left, we see the way it was when it was published. On the right, we see the way that NED has standardized them, where they have put the wavelength instead they've converted it to frequency, and then they put the in hertz, then they put the intensity in watts per meter squared per hertz. In optical astronomy, we tend to use wavelength instead of frequency, so it's easier for me. I'm going to use this on the left. So we have the spectral axis, means the wavelength in angstroms. The intensity is the flux density, ergs of energy per centimeter squared of area per second of time, that'd be flux, and then per angstrom of wavelength, that's flux density. In many cases, but not here, you'll have the error or uncertainty in those intensity values, and you can use that to get error bars, but we don't have that for this. Now, we're going to save this file. You can just save like that, put it in your folder, and then we're going to open it up in a spreadsheet. You can also do it, I know that they've trained you in using TopCat, and you might be able to use it in TopCat here. I've been doing all of this stuff in spreadsheets, which is also convenient for doing the other calculations there, so I'm going to do it this way. All right, so open it up. You can simply import it as a text file, and all you need are those first 2 or maybe 3 columns, and then you can copy that over onto a page where you've got the calculations. Now, the way I've arranged it here, first always label which quasar you're using so you don't forget. And I have gone on and made the labeling really fancy, but these first 2 or 3 columns are just where I've copied the wavelength, the flux density, and the error there. Now, we've got to do some conversions. You see, the thing is that this is at a redshift where it's moving 16% the speed of light away from us. We know that those wavelengths are redshifted. In order to do the calculations, we've got to get it into the reference frame where we're moving along with the quasar, because that's what all the physics deals with, is the reference frame. So we need to apply some cosmology or some Doppler shifting. The equation is pretty simple. We take, actually, let me go back to my the book chapter. Okay. So we've got that equation there. I'm also going to go through, this is the same stuff that I've just shown you. All right, we're going to do the cosmological corrections here to go from the observed frame to the source frame. So those factors of 1 plus z are important. This is the basic equation here. The observed is equal to 1 plus z times the source. Now, but we need to solve for the source wavelength. So we simply divide what we observe by 1 plus z. All right, so I would recommend that you put a little a cell, as they call it here, with your redshift over here, 1.158 in this case. And then to get the source wavelength, you've got the cell where you have the observed wavelength divided by parentheses 1 plus, and then you reference this one. And if you're using a spreadsheet for this, to keep it where as you copy this down, it always goes to that same cell, you put a $ in front of the column and the row there. And that'll give it what's called an absolute reference where it doesn't change it. You can see here that the next one down is still referring to P11 like that, but everything else changes. Now, for the flux density, we have to do a conversion as well. But there are three effects that affect the flux density. There's time dilation, so the rate at which we receive the photons is slower than at which they were emitted. This reduces the flux by a factor of 1 over 1 plus z. The energy is lower as well, so that reduces it by 1 over 1 plus z as well. But then the bandwidth is wider. So if you look at the flux density per range of wavelengths, that delta lambda is wider when we observe it and narrow where it's emitted. That would increase it by a factor of 1 plus z. So the net effect is that we get an overall decrease by 1 over 1 plus z. So the source flux density divided by 1 plus z gives us the observed. We turn that around, solve for the source, and we're going to multiply the, whoops, that's an error there, by the way. The source density is equal to 1 plus z 1 times, that should be the observed flux density. So make a note there. All right, so we'll do that in the spreadsheet as well. You can see my flux density here is the observed flux density times 1 plus z. All right, now we're in a rest frame, we're in the frame of reference of the quasar. We're moving along with it, but we're still at a great distance away from it. Oh, let me show you. I have plotted flux density versus wavelength for the observed and for the source frames. And I put that in a separate tab here. Those tabs are really handy. In the observer frame, we saw it like this. Look at the wavelengths. But if we plot the source frame, you see it's shifted over to the left to bluer wavelengths. Well, that's what you would see if you were right there. All right, and that's what the frame that we work in. But we need to calculate, and we could do the H beta line width in the source frame without doing any more conversions, but we need to get the luminosity at 5100 angstroms right there. This is not luminosity, this is flux. Okay, so we need to do a geometric correction. So we're seeing the light spreading out in all directions evenly in the shape of a sphere. And to get luminosity from flux, all right, luminosity is the flux divided by the surface area that light is spread over. Or you can think of it in terms that the flux is the luminosity, the power, the wattage of that quasar spread out over the surface area of a sphere at whatever distance we are from the quasar. So if we're a distance d from it, then the sphere has a radius d, and the surface area of that sphere is 4 pi d squared. All right, so the luminosity is the flux divided by 4 pi d squared. Now, we're looking not with luminosity and flux, but with luminosity density, flux density per unit wavelength. Well, that is defined as the derivative of flux with respect to wavelength, or derivative of luminosity with respect to wavelength. And the same equation holds for them too. You take the derivative of both sides, you get it. So that works out very nicely. Flux density is in these units, ergs per second per centimeter squared per angstrom. That means our distance to that quasar has to be given in centimeters. That's going to be a lot of centimeters. But, well, it's not really much crazier than measuring it in meters. It's still an astronomically large number. So we need to calculate. We can look up the distance in terms of centimeters. Now, what is the distance? We've just got the redshift. So we can go to, if you go to this website here, that's on the NASA Extragalactic Database again, there is a list of what are called cosmological calculators. I have made this an embedded link. So you just click on that and up comes in your web browser, the list of cosmology calculators. I tend to use Ned Wright's. It was the first one I ever used. And he makes a nice little widget that goes on a Macintosh where it comes up on my main desktop. All right, so what we do is he's already got it by default with the current value of Hubble's constant, the density of matter in the universe, the density of the vacuum energy of the universe. This is all in cosmology. And then he's got just a redshift. All right. So you put in your own redshift, 0.158. We looked that up, remember. Now don't hit enter. You've got to say, is it an open universe, a flat universe? Just hit general, because he's already set the densities of these here. And I can't go into the cosmology, unfortunately, but just hit general, which, by the way, is set to flat. That means the density of the vacuum energy plus matter adds up to 1. You hit general, link. This frame on the right reloads. Check to make sure it's got the redshift that you had. And it gives you a whole lot of distances here and scales and so on. What we want is called the luminosity distance, d sub L. And in this case, it's given in units of millions of parsecs, megaparsecs. But that, by the way, GLY is giga light years, billions of light years. So we want it in megaparsecs, 760.5 megaparsecs. Now, put that in on your spreadsheet. Again, spreadsheets are great for just doing a lot of calculations, but you might also write up, say, a Python program or something. Let's see here. So I've got my cosmology worksheet. Put that in 747. I said 760. All right, let's put 760.5. I think I looked up a redshift for it. That was an older, out-of-date redshift earlier. Oh, I see. The one that I've been using for it had a different assumption of Hubble's constant and gave a slightly different result. So I put in the conversion to centimeters. Now, if you're not sure what that conversion is, a great website for converting things is, I was looking at what time my talk started here in Indian Standard Time. I know we're getting close on the time, but we're almost done. Is Wolfram Alpha. wolframalpha.com, and you just put in like 1 megaparsec in centimeters. And it makes sure it understands what you're trying to write. Stephen Wolfram, by the way, is the guy who created the Mathematica language. Make sure it did that correctly. And here you get your conversion, and you can get a plain text version here, which we can copy and paste. And that's where I came up with my conversion factor. Double click on that, and I just multiplied there. And I've kept constants and conversion factors up like that. All right, so now we have the distance in centimeters, 10 to the 27th power, boy. All right, so now we've got that cosmology ready to go. Now, let's see, I teach you how to use that there. And now we need to measure, we need to put it into the luminosity. So we're going to take L sub lambda and we multiply it by the wavelength for every individual data point. All right, so let's look at here. So luminosity density, which is the easiest to do here, that is just 4 pi times the flux density, 4 pi times the distance squared. There's the distance in centimeters, quantity squared. Make sure you keep that as an absolute reference with the dollar signs, so it doesn't go and try to shift down to different cells, times the flux density. All right, so we get that. That's the luminosity density, and we can plot that spectrum, but let's go on and multiply that by the wavelength. Make sure you multiply it by the wavelength in the source frame, not the observer frame. Okay, we got that. And now we just copy those formulas down and we get the luminosity graph. Now notice I said no smoothing. See, I'd worked with a different one as well, which was a very noisy spectrum. And let me see if I can pull that up here real quickly. This is one of the Seifert galaxies that I'm writing a paper on. And I was testing the whole procedure out on that. Now, look how noisy that is. And that's when it's smoothed. So what I did was to smooth data. Now you lose a bit of spectral resolution, but I took the, to plot the luminosity at one wavelength, at that wavelength there, I averaged together the luminosity at the wavelength before it, at that wavelength, and after it. I averaged those three together like that, and then we just go on down. Now that means you miss the first one and you'll miss the last one. And see, these overlap like that. Okay, this is called a boxcar averaging for smoothing. And when you do that, then it does smooth it out. This was much worse before I did it. Here's the H beta line, and the continuum is right there. Okay, that's a rough one to do. Okay, in the case of 3C273, it's such a nice, bright quasar that we don't need to do any smoothing. Here we see H beta, there's O3, H alpha, and the nitrogen 2 line there. Now, what I recommend doing is you plot the whole thing first so that you get a sense of what it looks like. And you can see where the continuum points are. But then I recommend zoom in on your H beta line and on the continuum line there. All right, now, when I rescaled that, it went off. And plot the grid lines. And what I'm going to have you do is to print these out and work on this by hand. So the maximum, let's go to 1.6. Okay. So now we see I've roughly centered it on the H beta line, and I have spread the limits here to the left and the right so I can pick up the continuum. And you really have to get a better sense of it from the overall graph. That goes back down to the continuum here and here. But notice that that oxygen 3 disturbs that a bit. So now, and for the continuum luminosity here, notice that's also the H beta line, or that's the, what is that? That's the O3 line there. Here's 5100 angstroms. There we're at the continuum level. You can read off the continuum level just by putting your mouse over that on some operating systems. And we can read off that it's 7.519 times 10 to the 44th power. And we just write that down. And that's ergs per second. Now for the H beta, it's trickier. What you're going to do is you've got to account for the continuum. You've got to find the maximum and the full width at half max. So let me pull up. What I've done is I have printed it out, and then by hand. Now, this is not really the proper way of doing it, but this is what people did before you had the computers and you could do computer models of these line shapes. I have marked X's where the lines go back down to the continuum level. And again, you need the wide context to see that to make sure. Don't just zoom in to do that. But I made sure that that's where they were. Then I took a straight edge and I drew a straight line, and that's the continuum. Notice the continuum is sloped here. That's important. Now, from the continuum level where the, I also drew the H beta line at 4,863 angstroms, vertically down through here with a straight edge. That's why the grid lines are so useful. Now, from the base where the center of the line crosses the continuum, that's your base, to the maximum, I counted up the grid squares until I got to the halfway point, and then I drew the full width at half maximum from the left to the right edges parallel to the continuum there. Because if we subtracted the continuum, you see the entire shape would twist just a little bit. So the full width at half max is where we go along that diagonal there. And that requires a little bit of practice with your straight edge to make sure it's really parallel. And then I measure the wavelength of the left and the right sides. They're not necessarily symmetrical, but they'll be close in this case. And I enter in, you calculate delta lambda between those two. Okay. So over here, I've done the calculations in the spreadsheet so I can change them easily. I've got the red, that's the long wavelength side, and the blue, and I calculate the difference between them. It's just one minus the other. So it's got a width of 108 angstroms. Now, how do we get the velocity? See, we need to convert that to velocity. For that, all right. Let's see, we've already calculated our, let's do the broadline region radius first. Here's our equation again. In this case, I had calculated the broadline region luminosity, the continuum luminosity to be 7.3 times 10 to the 44th. Let's see if that's still right. Nope, it's a little higher since I recalculated. 7.556 times 10 to the 44th. So that's 7.556 E44. That's a way of writing exponentials in a spreadsheet. There we go. I've made the equation that converts that into the log of the radius in light days. Then I exponentiate 10 raised to that power to get it the radius in light days. And then I do the conversion from light days to meters here. We do want it in meters rather than centimeters because we're using the gravitational constant in terms of meters. All right, so that gets us that. So now we have R. Now we need to get the broad line velocity. So to convert between the full width and half max in units of angstroms and to get it in terms of velocity in meters per second, we use the approximation to the Doppler equation for low speeds, where the velocity of the gas is much less than the speed of light. I'm not talking about the redshift here of the overall quasar, but the motion of the broad line clouds. They are not moving at near light speed. At those speeds, the fraction of the speed of light you're moving is about equal to the range of wavelengths, fourth and half max, divided by the source wavelength, which is h beta in the rest frame. Solving for V, it's approximately the C times the fourth and half max in angstroms divided by h beta in angstroms. C will be in meters per second, 3 times 10 to the 8th meters per second. Okay, and doing that, I convert 108 angstroms of fourth and half max into a velocity of 6.66 million meters per second, which is pretty fast. Now, putting all of that together, we put that into our equation back. I had that way back up here. Scrolling. Oh, sorry, I put that into the PowerPoint. I haven't copied it into the chapter of the book yet. I'll send an updated copy to Priya when that's ready. All right, putting all that together then, I estimate a mass of 1.28 times 10 to the 39th power kilograms. Let's zoom in a little here. Can I? Oh, oops. Undo. Oh dear. All right. I hope I didn't change anything there. I wanted to view this larger so y'all could see that a bit better. Okay, that should be better. So what does that mean in kilograms? Well, we want to get it in terms of how many times the mass of the sun. That is our standard way of measuring the mass of a black hole. So you look up, you can use Wolfram alpha again, the mass of the sun in kilograms. And then we just do the conversion there. All right, this is 6 times 10 to the 8th solar masses. Now that means it is 640 million solar masses. So it's a little less than a billion. Now in American usage, a billion is 1,000 million. I know in British usage it may be different. And so I might ought to avoid the word billion, but this is, well, 6 times 10 to the 8th solar masses. Is that reasonable? Let's take a look here. If we go to a web page, you can look up, well, not there. Let's just go here, all right? Mass of 3C273. Now, this is a very well-known one, and therefore it'll have a lot of masses. Wikipedia for quasars, this actually has some useful stuff. 8.8 times 10 to the 8th is what they say. And what we've come up with is 6.4 times 10 to the 8th. Well, does that mean we're really badly off? No. That means we're actually doing remarkably well because black hole masses are honestly kind of there's a bit of black magic that goes into them. The uncertainties, the systematic uncertainties are just enormous. The precision that we can get is if you measure the logarithm of the black hole mass and the logarithm of your error, it's like plus or minus 0.4 dex, DEX is how we say logarithmic error there, which means in terms, it's the logarithm of that plus or minus like 0.4. Maybe it's been a little bit better lately. And we're doing it where we're not even modeling that Gaussian curve, which would be the proper way of measuring full width and half max. We're doing it by eye, and we can be thrown off. And yet we came up with something that's within 20%. Less than 20%, I think. well, close to 20%. That's really darn good. I would expect normally to be within a factor of 10 would be good, but here we're very, very close. And you can calculate uncertainties more precisely. Now, what about that, that narrow line region I was telling you? So we've got, let's take a look at this galaxy here, where you can see just barely, there's the broad component, and maybe there's a little narrow component sticking up from it there, because we do have both in many cases. Sometimes the narrow component is brighter, sometimes it's very weak. It's kind of hard to tell unless you've got a very good spectrum. Now, for 3C273, it looked to me like it was dominated by the broad. But in this one, I think that little peak there is narrow. I have zoomed in on that, and I have, in fact, I'm going to pull up where I drew the graph by hand. Let's see, where did I put that? I think I've got my annotated ones over here. Yes. Oh, but I have to straighten it. Okay, and I am just about finished here. All right, in this case, I estimated the continuum to be like that. And what you do is you try to use a little bit of artistic skill. Try to, if you see where the narrow component appears to be, figure where the bottom of that is and say, all right, that's the top of my broad component. And I'm going to try to draw a, let's say it's a Gaussian, try to draw that bell curve so that it goes from the little x's where it meets the continuum, and it goes up to the maximum there, and I smoothly fit in between. Now, I'm also trying to average over those random jumps up and down. That's the noise. And I try to get it running through about the middle of those, although because there is also that 03 right there. So I kind of ignored that. All right, and then I estimated that the fourth and half max was here rather than higher up. If I had assumed that that tip was really the maximum, that would have moved this upward and made it appear to be narrower, which would make me assume that there was a lower mass black hole. In this case, I think it's a bit wider here. Now, the proper way to do it is to fit two Gaussians or two Lorentzian curves to it, but you can't do that very easily with a spreadsheet. You'd have to write a, say, Python program or get some IRAF has some software to fit that. That's a whole nother bit of training, which I can't get into here. So I'm showing you how to do it a simple, crude way. But even with this, I came up with a very close answer to which matched what I had done by other means that it took me about 2 years. So you can get a ballpark result pretty well. I believe that is all that I'm going to cover here for it. So Priya, I'm going to load up again this chapter, my whole maths chapter. Let me load that file so you can distribute it, and I will send in a more complete version of it when I've done some more editing. And I know they may be taking a while to go through their projects. So remember that there is that one typo as well. Okay, I don't know where, since we'd started a bit later, don't know where we are on the time, but I'm available for questions if we have time for them.
Thank you, Tim. I can see there are some questions.
Okay, I see one from, I'm sorry if I mispronounce, Satyaki. So let's see. What are the ways to find the occupation fraction?
What are the ways to find the occupation fraction or occupancy of AGN in clusters?
Okay, so honestly, I would do a literature search. And by the way, oh, sorry, one other thing here, because of literature searches. Where would you find, I mean, if you can find the spectrum on the NASA Extragalactic Database, where do you find a number, where do you find the names of quasars or other active galaxies in order to look them up? Well, I have given here, still sharing this here, I believe, literature sources for quasars and Seyfert galaxies, which are the two best kinds to use for this method. Both of them have bright, broad emission lines. The first is Varone City in Varone. There's a web-based catalog of basically every active galaxy that's been published ever. But it's so complete, it's kind of overwhelming. But you can look up anything, and it'll tell you what kind it is and so on. Todd Borson and Paul Green, I think, 1992, mission lines of low redshift quasars. I've given you the bibliography code. If you go to the NASA Abstract Database Server, ADS, you can put that in and look that up. Those are low redshift quasars. They're bright. They've been observed a lot. Lots of archival spectra should be available. Crenshaw et al. 2003, which is for narrow line Seyfert 1s. That's those where the broad lines are actually relatively narrow, which implies that they have smaller black holes. But they also have narrow line and broad line Seyferts. So that'd be a good project, comparing the masses of the broad and the narrow line Seyferts to see if they do seem to have different mass black holes, which we think that they do. And one, which scrolls over to the next page, this is one that's only a list of narrow line Seyfert 1s, but they've measured the black hole mass using X-rays, which would give you a comparison to see how your H beta masses compare to X-ray based masses. And because again, there's systematic differences. The quasar that I'm publishing on right now, we've got orders of magnitude difference between different estimates of the black hole mass. So now, sorry, going back to the question, occupation fraction in clusters. And look up on, simply look, do a literature search where if you go to the NASA Abstract Database Server, adsabs.harvard.edu, okay, they got a new version here. You can do a literature search here by the full text, just any words that are in the text. Although I recommend, to narrow it down, you do a search in the abstract. And so you could put in things like AGN. Oh, let's see here. We need to do, it's a little tricky to use the new system. But if we put in AGN and then we do, let's see here, we can put a phrase. How do I do quote marks? Okay, cluster and occupation, maybe like that there, and just hit enter. There are better ways of organizing the search like that, to do Boolean searches and so on. So you can do things like this here, and I don't know an answer for it. Typically, you're going to get maybe one active galaxy in a large cluster, dominated by one at the center of the cluster. But you may have some other kinds. And there's even been some results for dwarf galaxies that might have an active nucleus there. Let's see, how are off-center AGN distinguished from regular ones? Now, in this, do you mean where the nucleus is not centered on the galaxy?
I guess so.
Yeah.
I guess so. Yeah, is it off-center in the cluster or the AGN is off-center? I'm not too sure. Who is this asking? I can't see the name, but you can unmute yourself and ask. Okay, Satyaki, you were asking, what do you mean by off-center? You mean to say off-center in the cluster, or the AGN is located off-center?
Like off-center in the host galaxy, say.
Yeah, I don't know. Where is he? Satyaki. Are you there, Satyaki?
Ah, okay. So off-center AGN in the host. Ah, yes. In fact, in my my PhD dissertation, I was working on low redshift quasars with the Hubble, and we did have a couple where the nucleus was off-center from the host. Those typically are in interacting galaxies, in mergers, and in those cases, you expect over time that black hole is going to settle back down to the very center through what's called dynamical friction. And eventually it will be in the middle, but it might take, maybe it takes 1 billion years for that to center, maybe a gig year. So those would probably be a signature of a recent merger. Okay, let's see here. And you also ask some experience studying Seyfert 1 galaxies in the ultraviolet. Now, by the way, Seyfert 1, Seyfert 2, a number 1, type 1 AGN means it is clearly visible. A type 2 is obscured by dust. What would be the best wavelength range to study most varieties of AGN and why? That is a great question. There's not a good answer because every range of wavelength is useful for something about it. So for example, let's do optical. I work in the optical almost exclusively. If you're wanting to look at if you're wanting to do imaging, I would recommend optical, and optical to infrared is good for imaging. In order to see both the host and the nucleus. If you go into the infrared, the nucleus is a little bit fainter and the host is brighter. So if you want to see the host galaxy, that's great. It minimizes that contrast and that glare from the nucleus. On the other hand, if you want to identify an AGN without being obscured by the host, looking in X-rays is a great way of finding them. Maybe the least biased way of finding an AGN is by doing an X-ray search. If you want to do the high energy emission from the plasma jets coming out, X-rays and radio, and in some cases gamma rays are useful. Not so much for the Seyfert galaxies because those are usually radio quiet and they tend to be very low powered, not putting out those high energy jets. But a few of them do, which is what I'm studying right now, that even emit gamma rays. For spectroscopy, ultraviolet is important with the Lyman series. But also optical there are lots of optical lines in AGN going off into the infrared. Right now, I'm starting to pick up onto the mid-infrared, which is new to me. And unfortunately, I can't tell you much about what it's useful for in them. I think a lot of molecular lines are in the infrared. And then radio only for the radio loud ones there. Boy, it is a tough question. But optical is kind of a good all-around one, but every single wavelength will get you something.
So Tim, the student actually seems to have some network problem. So he actually wrote in the text that the off-center he meant with reference to the host. That's what he was referring. That's what you answered. Right?
In fact, I see right now, I pulled up the chat window for just that purpose there. So often one's in context.
That his network is bad, so he's typing his question. Yeah, he means off-center host.
Okay. And yes, those are generally a recent merger, which could be the thing that triggers the AGN to begin with.
So that would be a good, but you don't know where to start with, right? If you want to do the age of the interaction, you don't know where you started from, right? So that.
Well, let's see, we are kind of putting together a merger sequence of AGN where you start off with two isolated galaxies, which would be normal looking galaxies. As they get closer, you get tidally stretched out arms that would be raised there. That would be the sign that they're starting the merger. And then as it goes through, you get a real mess. And the shape of the galaxy may not be easily modeled by either elliptical or spiral. It might be just irregular. And the active nucleus may come up at that point. Also, early on in a merger, there's a lot of dust that's raised from star formation, and that can obscure the active nucleus, which means that you might start off with a type 2 AGN, like a Seyfert 2, which might be hard to identify because the dust blocks our view of the nucleus. So there's a lot of work going on now in order to identify obscured type 2 AGN so that we can see the early merger stages. And I would imagine the spectroscopy is very interesting because you should be getting a lot of stellar lines as well, O and B stars and nebulas too from the star formation, H1 and H2 emission lines.
And so sorry for jumping a little bit, but since we are not meeting more in this session, so what would you say would be the probable projects that students can do?
I think you could do like there was that that last paper here, Nikolajuk, Polish name.
Okay.
I gave a direct link to it there. This one, depending on the background level of the student, that would be a very straightforward one where you could measure the H beta masses. And then you could compare to the X-ray measured masses. If you do the Crenshaw paper, there's a nice list of both narrow and broad line Seyferts, and you could see whether the narrow and the broad line galaxies really do seem to have different mass black holes. But also, when you get to look at the different masses of black holes, if the student has some background with the imaging, like back in the earlier on in the workshop a few months ago, For those that had done some of the imaging, you can find Sloan images for the low redshift ones. Sloan might be useful. For higher redshift, you'd have to look to see what some of the archives like for the Hubble Space Telescope or other observatories. But if you can find images of it, look to see what the different kinds of galaxies might be. Can you find if there are spirals versus ellipticals? Seyfert galaxies are usually in spirals, but occasionally you find an elliptical. Is the nucleus brighter? So maybe the H beta line which tells you that, all right, this has got a more massive black hole. Well, there's a correlation generally between the black hole mass and its luminosity. So there's what's called the Eddington limit, which I didn't get into, where the maximum rate at which it can accrete matter is the Eddington limit. If it accretes faster than that, it gets brighter, and the pressure from the light itself blows the gas away from the nucleus, shutting off the fueling. So it's a self-limiting feature. So there are very few ways. It's hard to get it accreting faster than the Eddington limit, and that's simply proportional to the black hole mass. So it is generally expected that the lower mass active galaxies accrete closer to the Eddington limit. So these narrow line Seyfert ones we think are going to be accreting at nearly the Eddington limit, whereas a more massive quasar is probably accreting down like maybe, I'm trying to remember, maybe 1% of the Eddington limit. It may be brighter overall, but its black hole is much larger. It could support faster accretion, but it just doesn't. So you could measure, you could take some massive quasars, you could take some narrow line Seyfert ones, and if you can measure the black hole mass, calculate the Eddington limit, and then if you can isolate the nucleus, the point spread function of the nucleus, and get the luminosity of that, then you could see how close are they to the Eddington limit there. That takes more work, and it would take image processing and maybe using, say, GalFit, things like that.
Yeah, so the last, in Astronomy from Archival Data, some students did do GalFitting, but what we made them do was basic budge disk decomposition. Now they can add the PSF, the central one also, they can add the point source.
Yes, and so we're doing that. Now, one thing to note on that, the point source, if you have nothing else, you can try modeling a Gaussian with it. I'm trying to think if GalFit might have that option. You can actually, I think, create a very narrow component as a analytical model that you can imitate the point spread function with. But if you have stars in the field of view, you can cut out the star and use that as a point spread function.
Yeah.
Ideally, you would use the, this could be a lot of work, but there is DAOPHOT, DAOPHOT, which is in IRAF, and that can be used to combine lots of stars into a nice average PSF, which is a wonderful thing, but it takes a little bit of learning, a lot of learning for me. And that would make an even better PSF. Now, if you're using the Hubble's PSF is so stable that it's possible to make a theoretical model of it using software called TinyTim, and that's freely available online. But they also have a PSF library for some of the cameras. And unfortunately, I tried to look that up, and it looks like the web page may not be accessible right now. But that's something that can be checked. And you can simply download sample PSFs based on the camera you're using, where it is in the field of view, and so on. So there are ways to get those PSFs. The trouble is finding the PSF model that fits that kind of a camera and telescope you're using. It'd be a great project.
Yeah, no, actually, see, what we've done is, this is March, right? So the tentative plan is to have the next workshop in July. And so in principle, students get 4 months to work, in the sense April, May, June. April, May, June. Okay, if we do July end. And the ideal part is, what we've actually planned is, this new website actually has a forum page. So last time what happened is, interactions were quite scattered with WhatsApp and things like that, Telegram. It was mixed. Now I hope that now, since we have a forum page, people can put up their things over there, and the discussions can be more open and accessible for everyone. So let's see, we can try out these. So as I see, there are 3, right? One is the difference in narrow and broadline Seyferts. The other one we said was, oh God, what was the other one? The other one was,
you could be looking at, what did I say?
yeah, one was the gazetting
Narrow
thing.
broadline
And,
Sieverts,
oh, you said the X-ray emission, that third paper, X-ray emission with the hydrogen beta.
right. So compare black hole masses from two different methods.
Yeah. So
And
there are
another
three
would be
projects which I can put up.
looking to see how close to the Eddington limit these are emitting. And that would be good to compare quasars, which tend to have more massive black holes, with, say, narrow line Seyfert 1s, which have smaller black holes, maybe like orders of magnitude smaller, 1 or 2 orders of magnitude smaller.
Okay. So
If you can give a short write-up on the possible projects,
yes,
you can put it up in the group and then they can work on it.
Okay.
Yeah, some short note if you can give some directions.
Okay.
Yeah.
And there's one more question. What are cold cores in terms of active galaxies? What's that?
Oh, now that is a great question because I'm not really sure. Now I have an idea here. Let me move that out of the way here. That I'm not sure that I've heard the word cold for the cores, but it might be referring to John Cormandy, the University of Texas, has been working on the fact that in a number of kinds of galaxies, I think he's mostly looking at elliptical galaxies, the core, so you can fit a Cercic profile to a range of galaxy radial luminosity profiles. So how bright they are in the middle versus how bright are the outer edges. If you look just at that kind of a radial section of it there are different galaxies have the middle of it where they've got extra light and some have less light. And so one thing that I've been, okay, all right, I'm looking up here just in the literature. I see it's talking about cold gas falling into the core.
Yes.
I have not done any work with the gas transport myself, and so I'm afraid I can't go into that from any experience. But that's probably dealing with the flow of the gas throughout the galaxy. The only gas that really accretes onto the accretion disk is going to be cold, relatively cold. If it gets too hot, like X-ray hot, millions of degrees, it cannot accrete too easily. So, but they may be talking about a smaller range of temperature here, and I'm just not sure about that.
Okay. So, are there any more questions? You can unmute yourselves, people, if you want to ask something.
Thank you, Chetan. I appreciate it.
Yeah, no, thanks. It's been, I mean, it's great having you. And so that's what we were just talking about. Najam was asking me, why is Tim doing only one session? So I said, he thought this was the wrong weekend.
Yes, I was thinking that Easter changes every year, and I was thinking that it was this weekend, and we were going to be gone to my parents, and turned out it's not. It's next weekend.
Yeah, that's good. So,
but I'm glad it allowed me to do it live. It's much better than trying to do it taped. The interaction with the students is always good.
Definitely, that's right.
And the time was actually very good for me. It's a convenient time in the morning.
Yeah, it was just I just put it over there because I'd already set all the talks. So I just put this over here, and I thought that in case you can come, we can have it. It's at least day for you. So thanks, Tim. Thanks. That was a very nice session, and we look forward to seeing more of you. Like I said in our further Star Trek episodes.
Yes, and by the way, I now my camera doesn't really show it, but I made sure to wear today my my NASA polo shirt, which my daughters got me for Christmas, and I've been wearing this on when I'm doing public presentation days there.
Actually, we should have also got ourselves some Star Trek T-shirts.
Yes, and for the James Webb Space Telescope, very early on, it was called the Next Generation Space Telescope, which was directly a Star Trek reference, and Goddard Space Flight Center had as their own logo for the Next Generation Space Telescope, they made the little Star Trek little swoosh badge there, which I wish I had been able to get a poster of that had that before they changed it all then. That was pretty neat.
we thought that the Star Trek theme would be, catchy, good. We got a lot of young crowd around, so we have to keep them, involved.
And when I saw it, so I logged in. I registered on the site, so I can also see the chats and so on there. And I liked that you had when I saw the space shuttle profile on there, and it said Enterprise. I was thinking Space Shuttle Enterprise, which was the atmospheric test shuttle. But of course, that one was named for the Starship Enterprise. It was named by kind of a naming. I think it was Star Trek fans that convinced NASA to name it Enterprise for that reason. And when they had unveiled the shuttle back in the 1977, they had out the cast of the TV show to come out there to the shuttle for it. So there's a big publicity with that there. I remember that back at the time.
And I hope you noticed that on the website, the home button is the Earth.
Coming back.
Oh, yeah.
So if you want to go back to home, you need to click on the Earth.
Very appropriate there.
So we purposely didn't even write that so that let people guess it, Why tell them? They should guess it.
I did not pick up on that, and I should have. I like that.
So, okay. So thanks a lot, Tim, and see you soon. So we'll keep in touch. So the plan is that this is a slightly different format. The plan is that now, participants will have 4 months to work on it, so that the next workshop of the 3 days, at least one day we devote it to presentations by participants, so that it's more interactive. Otherwise, if it's only one way talking and, participants don't talk, it's no fun. So what we want to do is that they use this time to work, and accordingly, at least half the time in the next workshop would be presentations. Some kind of brainstorming where they could talk about how could they further improve on their projects and what more can be done.
Yeah, and we were hoping that by July we can meet in person. Some people can come over and.
I don't know. Yeah. I don't know how it's going to work out.
Well, I just got my first vaccination shot 2 days ago.
Oh, we got ours 2 weeks ago. We got it 2 weeks ago.
Ah, very good, very good. So now it's only what, 4 more weeks before I can go back to licking doorknobs and eating food off the floor and things like that again. So
no, but now they've come up with a new theory that you need to have a longer gap between your 2 shots.
They're doing 4 weeks per month. They're doing 4
so now
weeks.
we need to keep it 6 to 8 weeks, so it becomes a little longer for us.
Okay.
So
which one did you get? I got Moderna.
No. In India, there are 2. There's one called Covaxin and there's Covishield. So Covaxin is a Indian-made one, and Covishield is the one done with Oxford. So we have done that one, the Oxford one, AstraZeneca. But
my parents and now West Virginia, which I'm very proud. My state here of West Virginia is the 8th best in terms of vaccinating the population in the entire world. So we've been poor little West Virginia is actually doing very well, and so almost all the adults in the family have gotten vaccinated now. So. Looking forward to normal
India is
life.
also not doing too bad. There's actually much more supply than demand because a whole bunch of people are scared to take it, and they're not taking it.
Yeah.
So that's how even we managed to get it, because it's available. People
they were giving it for over 60, but then there were many people who wouldn't want to take it, so we could skip the queue. We went there.
Yeah, so all the best. Let's hope this thing is done soon. So we hope the July meeting would be a proper offline one. Let's see.
Then you can visit.
Yeah, and then you should visit us. We can have a longer session.
Okay.
Yeah. So see you. Bye-bye. Thank you.
Goodbye, everybody. Thanks for attending. I appreciate it.
Thanks a lot. Bye-bye.